All right, I want to make a video just going through what's happening in this question. So we have the radius r of a circular disc is increasing at a rate of 3 centimeters per second. And we want to determine the rate of increase of the area when r is equal to 4 centimeters. So what's happening here? So that we have a little animation. So what they're saying is that this radius of this circle, this green circle I have here, is increasing at a rate of 3 centimeters per second. Okay, so that's how fast it's expanding outward. Okay, and we're asked when the radius is 4 centimeters, so that's shown by this dotted line around the outside, right? So when the radius passes through 4 centimeters, how fast is the area increasing? Like what's the rate of the area of the change of area? So this is going to be what is dA dt, right? How is the area changing with respect to time? So as time is going by, how fast is the area changing? So if you think about it, if you back it up a little bit, right? The area, like as the radius is changing down here, right? At this constant rate all the way across, this 3 centimeters per second, the area is not changing that fast every second at this point, right? But then as it goes out, right, as the circle gets bigger, a little change on my radius makes a big change on my area because it's happening everywhere around the outside of the circle. So as you go out, it's changing its rate faster, right? So you actually have a changing rate. So dA dt is changing throughout this entire thing. It's accelerating, I guess. Okay, so when you do this question, we want to write down our knowns, right? Because it can get a little bit confusing, especially with examples we're going to do in the next part. So we know the radius is 4 centimeters, where we're interested in, right? The radius is actually changing, but we're interested right when it's at 4 centimeters. We want to know what the change in, or what dA dt will be, or the rate of increase of the area. Okay, so that's 4 dr dt. That's 3 centimeters per second, and that's 3 centimeters a second for the whole thing, right? That's the rate that this radius is changing. Okay, so that's a constant term, right? 3 centimeters per second. That's not changing at all. Okay, but then dA dt, that is the one that's changing, right? It's less here. It's actually a bigger number when we get to this point. So now what we do is we're going to start with the formula for a circle. So area is equal to pi r squared. And then we're going to take the derivative using implicit differentiation with respect to time. All right, so if we do that, then we just have dA dt, right? The derivative of a is just 1, right? But then you have to multiply by the inside. So you get dA dt is equal to, and then if we take the derivative of r squared, the 2 comes down, right? So we get 2 pi r, but then we have to multiply again by the inside. So dr dt. So there we go. Our rates just popped up, right? dA dt is the thing we're looking for. And dr dt, well, that's 3 centimeters per second. Okay, now that we have that, we can just actually plug in what we know. So now we're just going to substitute in our known values. So at this point, I'll leave this up to you guys.